Hello, are you uh, able to hear me now? Okay. So there was some questions regarding the switching logic for a BLDC motor. Excuse me. So I'll be covering that one um, before going on to this week's assignment. So I guess this week assignment is based on encoders. Um, uh, this week it's been covered with absolute and incremental encoders, and along with that, um, there is. Give me a second. There is also stepper motor, right? Okay. So, do you have any questions regarding the Boolean logic, Boolean expression? This was covered actually in last week, but there were some questions. People have contacted via mail. So I just want to ask, is the Boolean expression clear to everyone from the last week?
Yes, sir. Perfect.
Hello? Yeah? So you are able to understand how this expressions have come. Okay? All right. Oops. Let me just copy this. Yeah, we'll start with this. So we know the induced EMF that comes from a BLDC motor. So all this waveform that you see, uh, this red is where the flat curve of the induced EMF will be. This is what is indicated as red for the red phase, right? And the red line that is below the hall is indicated as negative, where your S4 will be active, right? So that is how this entire thing is shown, so that you can understand how we are getting the switching logic. So I'm just going through this. I'll be taking 20 minutes of this one, as this is hindering a lot of people. Let it go in recording. If there is any doubt, you can ask. If there is none, then well and good. Yeah. So yeah. So how motor construction is done for BLDC is that um, you like sir had explained, there is 120 degrees, 180 degrees of north pole. Here there is south. Here there is north. So unipolar. A magnet with one polar cannot exist. So this is another 180 degrees. But practically, you may not have something like 180, 180. You may have some other construction But based on that construction, again your waveform and everything will change. So let us just stick with this construction for understanding. Okay. Okay. So here you can see the red phase, your coil will actually be here, right? So I am positioning my H1 in the middle of it. Maybe few constructions will not have such a placement, and here in the Y you will have yellow phase throughout here, right? And this will be your blue phase. So something like this will be the motor construction. So this red phase will be 180 degrees. So where is my rotor starting at is this will be my 0 degrees. It will be 30-degree inside when um, the motor starts. Yeah. So here if you see, if you go from yeah minus 30 degrees, you will see that the red phase will start uh, having some induced EMF in it, because the magnetic flux is changing around that coil. So when are we operating the red phase is when um, I want to pull this part inside, right? So that is how this is going to rotate. So I'll be actuating my red phase to a peak when the center of north pole, let's take, this is the um, uh, line that bisects the north pole that is exposed to the coils, if that is aligning to H1, right? So that is till when I'll be actuating my red coil. And after that, so what happens at this point is that your um, yeah, if this is your red phase, your magnet is going to perfectly sit inside this, like this will be your entire north pole, right? North, here, south, this side, right? So now what is happening is that out of 180 degrees minus 120, you'll have 60. Here you'll have 30 degrees. Here you'll have 30 degrees. This is now stuck here. Now if I do anything to the red coil, it's not going to move. So what I'll have to do is switch off this one. If I want to continue rotation this way, I'll switch on Y coil. So that is how this Boolean expression is um, determined. So here you can see this is how the waveform are. So the first one is that my red coil should be active from 30 degrees to 150 degrees, right, of the rotor position. So here I can see that the Hall sensor 1 will still be active because this 30-degree will be crossing H1 at some point of time, and that 30-degree is here, right, this region. So that is where I shouldn't be actuating my um, red phase. Right? My red phase should stop here. I should not actuate it anymore. After this, I'll have to actuate some other coil to bring it here. Right? Yeah, I'll be actuating my blue phase. No, they will be together. From this, I'll have to actuate yellow phase. Okay. So yes, um, based on this, why would I actuate my yellow phase? You can see that this north pole 30-degree in the other side is in the yellow phase. So now when I switch on the yellow phase, it will attract this north and bring this entire pole here, given that red is switched off. If that is not, it's going to come somewhere in between and be stuck. So that is where these Boolean expressions cannot be malleable, right? So yeah. So how would I get this 150, 30 to 150 region? Is that I need the information of where my um, rotor is and where it is going to go. Like it is in H1, yeah, and it wants to go to H2, near H2. So I would be using H1 bar H2, right? Similarly, for S3, if you look at S3, when S3 will active, here again I want the um, rotor to come to H2, yeah, and um, where is it going? H3. So I'll get H3 bar. If you look at in the graph, um, H1 for, sorry, uh, I made a mistake. H2, it should go to H2, uh, whereas, yeah, it is, I want it at H2 and it should go to H3, right? So here you can see the H2 will be high in this particular region, right? And H3 bar will make it stop at 270 degrees. So like that you will get from 150 to 270, where yellow is positive, 30 degrees to 150, where red is positive, and then we look at S5. S5 again, it is at, I want it at H3 going to H1. So I'll get H3 dot H1 bar, right? So this is where blue is positive. For negative, you can just take, oh, okay, yeah, for negative, you need to take, like for S1, the leg is, for the red phase, positive leg is S1 and the negative leg is S4. You can see it is just converse of it. So S1 is equal to S4 bar, or the converse. S3 is equal to S6 bar. S5 is equal to S2 bar. So this is how we get our Boolean sequence. Understanding the construction is very important. If that is uh, that is changed, your waveform and switching logic will change. Yeah. So yeah, so this is the part where we cover for encoders, and this week, um, yeah, this week we'll work with something called encoders. Hmm. So these encoders, what they do is that they sense for position and velocity. Right? What type of velocity we are interested in is angular. Right? There is linear also. You can, the construction will change. Right? So for a position feedback, like absolute position, I would use something called absolute encoder. Right? I can use incremental encoder for position sensing, but incremental encoders. But I will have to be sure where I'm starting from. Then only I can get a sense of absolute, or else I'll have incremental position. Right. So these are the two types of encoders. Uh, encoder. Yeah. So let's first start with absolute. So for finding absolute encoder, um, yeah, what we are trying to do here is that we like what does the word encoder mean? Let's start from there. We are encoding some position information in a device. Right? So like we had hall sensors here, they given fixed position of your rotor. The moment I actuate my red coil, I know this rotor is going to come to H1 and stop if I give a flat pulse in the red coil, right? So from that I know that my motor is at absolutely yeah, from here 30 plus, from here there will be the 30 plus 90, there will be 120 degrees, right? So at 120 degrees I'll know exactly. So here we cannot have that kind of an approach because a hall sensor is quite big, and having such resolution for every other angle will be little difficult. Okay. Pratyush, hi, I was just covering this Boolean expression. I just covered it. Now I'm trying to cover encoders.
Okay.
So if you have a doubt, let me know. I can, after covering encoders, I'll cover this Boolean logic again.
Okay.
Okay, Pratyush?
Okay.
Hello.
Okay. Okay.
All right. So yeah. Um, so what absolute encoders, how they are made? Is it one, we have a motor, right? So any type of encoding has to be a rotary kind of a, arrangement. So for an absolute encoder, how it would work is that, let's take, I have a circle, I embed information in some part that will be my minimum resolution, right? Let's take, this is 10 degrees. So for 10 degrees, I have to cover 36, right? So what is 36? Okay, I will not have something like a digital value. Let me take 2 power 4, right? 16. Yeah. Yeah. 4, 8, 16. Yeah, 16. Okay. So here I will have 16 quantizations like this small pies, right? Pieces of pie. I'll have 16 of such um, regions that will have specific information. Like this region can have 2 power 4, so I'll have something like 1 0 0 1, right? So this will be something like 0 here, 0 here, 0 here, and 1 here. Let me give another color, right? And my placement of anything that senses this, it can be a contact base, like there is a, let me use another color. There is a conductor here, right? So the moment I get 0, right, there is no conductivity, and there is only conductivity here, right? So I get 1 here, 0 0 0, something like this. It can be conductivity based, or it can contact based. This is contact based, or it can be optical, non-contact, right? So here I'll have something like slots. That pi will have region that is completely opaque, and this is where light can be allowed, right? So this will be like 1 1 1 0, and then negation of this will be 0 0 0 1, right? Something like this. Or it can work on this being transparent and other two being opaque. So this is about absolute encoder. So at any given time, wherever my rotor position is, will always be detected by a small region that is fixed to an inertial frame, right? Like my motor, there is one thing that rotates, the other remains static, that is stator, right? By this optical arrangement will be precisely calibrated and kept on the stator, right? And the disc will be moving with the rotor. So this will be the load end, this will be yeah, drive end, non-drive end, yeah. So in the non-drive drive end, I'll have something like an absolute encoder. So this is the concept for absolute encoder, and then I'll have incremental encoders. What happens with incremental encoders is that I'll have a disk, right, with small slots which will have signal passing from, we'll have something like this. And let me make a gap. This is a cross section view. I'll have an emitter, I'll have a detector. The moment I get a signal, this gives me a flat signal telling that it has crossed this particular hole. Okay. So with this I can find the pulses. So with this pulses, such pulses, I can say that the number of pulses that I get in a certain time interval, I can calculate that because I have manufactured this pulse to be, let's take 0.1 degrees, right? So if I encounter 4 pulses in, let's take time 3 seconds, right? So this 4 pulses, this is 1, 2, so distance between any 2 pulse will be 0.1 degree, right? No, actually it will be, so this will have 0.1, then there will be a gap of 0.1, and then there will be 0.1. So let's take pulses are something like this, right? So in 3 seconds, if you are getting 4 pulses, so you can see that one pulse is 0.2 degrees. So I'm getting 4 pulses, that will be 0.8 degrees in 3 seconds. That will come out to be, you can do the math, you will get something like 0.2, right? 2 by 3 is 6 degrees per second. This you can convert radian per second. So now here we would reduce this time interval dt as some frequency that doesn't hamper my um, electronics that is attached to this. So that what I mean by that is that most of my clock frequency is not occupied in determining my encoder, or there is a specific uh, chip IC that is made to record this value, right? Either or. I can reduce my dt to a very small value. So given with that small value, I can always get omega as a function of time, right? Instantaneous omega I can always find, or this omega will be in that dt, right? So I can always integrate this, as this will be a time series, I'll be able to integrate it. I'll get d theta, integral d theta is equal to integral of integral of omega, that is a function of time times dt, right? So here you can see that since this indefinite integral, you'll have theta plus actually you'll have del theta, that will be equal to omega del t, right? So here this del theta will be from theta, like the n theta, del t. Yeah. Okay. Okay. Let me just put it. This is the expression that you will get the del theta that it has moved at that del time. Okay. Delta time. So now, if we are interested in taking the absolute position, some drives have the initial position recorded and calibrated. Based on that, we can add this del theta with that predefined theta to get the absolute position. Right. So this is for encoders, and in stepper motor, what the construction is that it works on the principle of stepping. And how do I do this? Is I have a stator that has some coil that is wound on it, right? And this is arranged in a really fine spacing between them, right? And then my rotor also has such structures, right? And what I do with this is that when I actuate this coil, right? When I actuate this coil, this one will align. If it is somewhere here or here, it will align to this coil, and this is what we call stepping. Once it is aligned, and after that we can give a stepping diagram that actuates multiple phases. You would have heard something called bipolar stepper motor. So it has two phases. So those two phases will be alternatingly arranged like this. This will be one phase, this will be second, two, sorry, one, two, one, two, something like this. The construction internally it will be, and then you can see that when I'm actuating one, it's going to go to uh, like, let's take my rotor is something like this, right? So this is going to align here when I actuate one. The moment I actuate two, this is going to make a shift something like this. Since I have how many spacings? 1, 2, 3, 4, 5, 6. 360 degrees by 6. We'll have uh, 6, yeah, 60. So 6 divisions, this will make a 60-degree rotation, right? Because of switching coil 2. Then when I switch coil 1, again this will come here, and then it will keep switching. So the moment I have given some inertia to this, so moment I have given some momentum to this, it is easier to switch between and maintain a direction of rotation. So this is the concept for stepper motor. I guess most of the problems this week are based on you can draw the circuit, and you can find the armature voltage and armature current that I have covered past 2 weeks. So is there any other doubts that I can take up before I address Pratyush? I guess there are only two people here. Okay. Hmm?
In ESMS, uh, okay,
Sorry?
wait a second. Yeah. in permanent PMSM,
Yeah.
we need a sinusoidal voltage. Okay, by using the what do you call pulse width modulation, by
Yes.
adjusting the width, we can find the what do you call uh, a sinusoidal waveform, but it doesn't provide the negative slope. So we use SPWM. Correct.
Yes.
I have one question that do we provide that what you call triangular waveform for that externally from external side?
Yes. We give the triangular waveform, right, to actuate our MOSFET
Okay.
so that we get the pulses for. There is a comparator, right?
Yes, yes.
So you'll have
One reference will be there
one
and one
reference will be your
uh,
sinusoidal.
sense. Okay.
So the moment you see that, okay, I just erased. Let me just go back. Yeah, so how this works is that the moment sign or the positive terminal,
Hmm.
let me just put it this, when the positive is greater than the negative port, it will
Hmm.
give out this positive. That is a comparator. Yeah. So
Correct.
here you can see that moment my sine wave is something like this, right? And yeah, so my sine signal is above negative in this region, so it's going
But
to give
how,
that.
excuse me, but how can we consider the reference as a sinusoidal form? It means in this person, it means we are using that pulse width also in this.
Yeah, so that pulse width
This,
is coming from your triangular wave.
yeah, yeah, that's okay. It means earlier sir told that we use SP, what you call, yes, yes, SPWM
Yeah.
because we can't be able to find the negative slope. So that we are using that PWSM. But my
I
question
may
is
be
that
not sure about that statement, or that will be told in a context. Okay, let me just note it down. Okay, I'll send you a mail after this.
because after varying the width of the pulse, we can somewhat find the upper half of the sinusoidal waveform. In order to get the lower one also we use that sinusoidal pulse width modulation. My
Okay.
question is that that's reference we are taking for the
Yeah.
comparator.
Yeah.
Reference is somewhat upper. It means what you call. It is the upper half of the sinusoidal waveform. It means that that reference is coming from that by varying the pulse width.
Okay. I think I don't get your question. Let me get back to you. Okay. So your question is that in SPWM, first
SPWM
was
reference.
Y sign, right?
No, yeah, that's no. My question is that the reference, whatever reference we are taking, that for triangular waveform,
Mm-hmm.
is a curve. That is the
Yeah.
upper half of the sinusoidal waveform.
Okay.
That's coming from the by varying the pulse width or not, or it is another one.
Okay.
That's my question.
Uh, upper half.
On on that
Of
basis,
the
we are
yeah.
drawing the pulse width. No,
Yeah. Okay.
that's coming
Upper
out.
half of the reference um, is coming from SPW, right? This is what you are asking. Is it coming from?
No, there here two things are there. Na? One
Yeah.
triangular waveform is there and one reference is there,
Yes.
overlapping the what you call waveform. My
Comparator.
question is reference. Whatever we are taking the reference,
Okay.
that is somewhat in the form of a curve. Na?
Yes.
That's what I am asking. Where it is coming from? Is it coming from by varying the pulse width?
Okay. I understood your question. Where is it? This curve, right? Where is it
Yeah,
coming from? That is
yeah,
what you are
correct,
asking,
correct,
correct?
correct,
Okay.
correct.
So let me get back to you regarding
Okay,
that. Okay.
okay,
I'm not really sure. So let me just recheck and get it back. Okay.
okay.
Okay. Apart from that, Pratyush, is the Boolean expression clear, or
Uh,
I'll explain
whatever,
again?
thanks for that mail.
Okay.
Actually, I got confused with that north and south, but whatever expression I have sent you,
Yeah,
I I just sent on the basis of the boolean. It's coming from just writing the
just the
for every
Boolean.
30 degree.
Yes.
We can get the 100 on that what you call binary code, binary gray code. We are sorry gray code we are getting. On that basis, I have written this switch expression.
Yeah.
Can you explain that what you call north and south?
Yeah. Yeah. That one I'll do. Okay. So I have given you a little different construction that also works. Okay.
Okay.
So I'm just taking source construction. Okay. So that you
Okay.
don't, switch between multiple references.
Okay.
Okay. So here, um, yeah. So first thing is that let us understand where is the initial position of the rotor,
Okay.
right? So the initial position is somewhere here, right? This is 0 degree of the motor.
Can you make the cursor little bit? It means where it is going. I can't able to see that.
Okay.
Little bit.
Let me put something like this,
Oh,
highlight.
correct. Correct.
Okay. This is
Correct.
a 0 degree,
Correct.
right? So
Mm.
in 0 degree, what is happening is that, okay, let me just put it here. This is my 0 degree, actually. Okay.
Okay.
So it's something like this, 0 degree. So after 30 degrees, so this is also something that sir had explained, that after 30 degrees, it's something like I'll detect north. Okay.
Mm.
So let us assume some motor has such a construction.
Mm.
Okay. So this 30 degree
Mm.
is what is the initial lag. So now what is the output of my Hall sensor? How does a Hall sensor look like? Hall sensor is like a small sensor that is going to tell whether a north pole is near it. Okay.
Okay. Correct.
So something like this. Small sensor is there. It is going to tell me north pole is there or not. So you know after 30 degrees north pole will come here,
Mm.
right? So it's going to give me a one signal.
Correct.
Okay. So here is my one signal. Now
Mm.
if you see, till when, let's take that motor is rotating. You are rotating by hand this
Mm.
direction,
Mm.
right? And I want to see how the Hall sensors are giving the diagram, right?
Mm.
So now when I keep on rotating, Hall is going to give me perfect one for next 180 degrees, because my north pole is for complete 180 degrees.
Wanted to say so.
Okay.
Correct.
So now for initial 30 degrees there is nothing, and
Mm.
then for 120 degrees, right, from 0 30, uh, yeah, yeah, 120 degrees, how it will look like. My north pole would have perfectly be sitting, or it will be perfectly in front of H1,
Correct.
right? So it
Mm.
has covered 30 degrees and
Mm.
then 90 degrees, which is half of north pole,
Mm.
right? So it will come exactly in front of H1,
Mm.
right? And
Correct.
here you can see that the moment it was going there, this part of north pole was
Mm.
interfering with Y coil.
Mm.
There is where that EMF was generating.
Mm.
So here you can see that here from this point EMF was increasing. Induced EMF in Y was increasing. So I have
Mm.
given this notation. You can see that red I have given here. That means this is positive, this is negative. Below the Hall sensor, anything I have given, it's negative. And for H2, this is positive, this is negative. And why I have given H1 red, H2 yellow, and H3, why is that? Because they are
The three
at the
phases.
same region, right?
Okay.
So now you see, that when this is at 120 degree, this is perfectly sitting here. Okay,
Hmm.
Pratish?
Correct.
Now what I want to do is move this further. How will I move it? Let us take manually. I'm not moving. I have to switch off red
Hmm.
and turn Y.
Hmm.
Right? If I make this positive, it will try to pull this north pole.
Hmm.
So, yeah. So
Correct.
this will continue rotation in that way. So that is how the switching is going to happen. Right?
Okay.
So now if you see, I'm not only going to um, switch on Y, I'm also going to put negative in blue.
Hmm.
Right? Why? It attracts the south pole.
Hmm.
Right? You can see a couple is coming in and it will start rotating. Right? So this is that logic. So if I have to come to a Boolean expression
Okay.
without looking at maybe H1, H2, H3 logic,
Hmm.
so how I can think of it is that um, my switch 1 should be active till this 120 degrees.
Hmm.
Yeah,
Correct. Hmm.
actually this is 150 and
1 over
30
30 plus
30
120.
plus
130.
120. Sorry.
120. Hmm.
Yeah. So yeah, it should be active till this 150 degrees, and after that it should be switched off, and there will be another thing that will pull it. So if I look at H1, sorry, S1, so the red phase has to be active till the north pole comes to H1,
Hmm.
right? And from H1, where is it going? Towards H2,
Correct.
right? So I will have something like H1 dot H2 bar, because it
Hmm.
has to go to S2, H2,
Hmm.
right? So it can like this should be switched on till the rotor position has reached 30 degrees into uh, Y coil,
Hmm.
right? So that is where my H2 information is important, because the moment it is more than
Hmm.
little bit more than 30,
Hmm.
then uh, Y2, sorry, your Y region will have induced EMF.
Okay. Okay. In that H2 will come.
Yes. And if you take more than 30, right,
Hmm.
induced EMF in Y, I'm not saying H2. H2 will still be zero. If you
Okay.
take little more than 30, the moment you are 60 degrees, it
Hmm.
will come to H2. But here you know that this is also 30, this is also
Hmm.
30. The moment you have gone 30 more, you are leaving H1.
H1. Okay.
So that is where it should be H1 dot H2 bar, because just after 30, this 60 degrees that we have made, 30 plus 30, just after that, it is H2 is going to give me a positive signal, and
Hmm.
H1 is going to like here, if you see, I have moved 30, I move 30 more, I'll come here for the next 30, it will be out of H1, right? Here you can see
Correct.
30 plus 30, it will be out of H1. But my red coil should be active till 150 degrees. 150 degrees. Right? After that, I should not make it, or else while it is going, this is going to provide deceleration to it.
Hmm.
Right? So that's why I'll have S1 as H1 dot H2 bar. It should be at H1 and it is going to H2. Okay.
Hmm.
Same if we look for another coils, positive leg, you will have H2. It is at H2 and it is trying to go to
Okay.
H3,
Okay. I got it.
H3 bar.
Okay.
And then if you look
It is
at,
somewhat the
uh,
position of the rotor, North
yes,
pole and South pole, with respect to the Hall sensor.
with respect to horizons. Yes. So now you'll have S5 which will be H3 dot H1 bar, right? It is at H3 and it needs to go to H1 bar. And how would you get the negative leg? You do S1 bar is equal to S4, S3 bar is equal to S6, S2 bar is equal to S5. Okay,
Correct.
so this is how you will get the entire expression.
Oh,
And this will work, mostly it will work if your arrangement is similar. Like we have 180 degrees. If I give you a 30-degree arrangement of north and south, it will still
mhm.
work. Maybe frequency will be different, omega will come out different, but it will work. If you have 60 degrees, it will still work. Like I had shown, I had mailed to you, right?
Yeah,
That will
yeah.
also work. So you can have different constructions. The moment you have multiple north and south pole, maybe
Yes,
your
sir.
omega will change, your frequency will change, those things. Right? More the number of poles, your frequency will double.
Hall sensor will also be increased again.
No,
Mm.
hall sensor you can increase. Look, you can increase number of hall sensors, but they are not going to give you any switching diagram that will be different. It will only give you a position accuracy. When you want a smaller motor, which is PLDC, and you cannot put more than 3.
Correct.
Mm. So that is the physical limitation. You can have multiple hall sensors, but they are not going to help you. It's going to be the same because the period is reduced. You can understand that.
Correct. Correct.
Okay?
Really
Now it
good.
is 0 to 360. It will
Mm.
reduce to 0 to 120 if you double the number of poles or
Correct.
triple. Sorry. So this is the expression behind that thing. I'll get back to you about this question.
Yeah.
Okay, how sir has explained SPW,
Okay.
and I'll send you a mail maybe today or
Okay.
tomorrow evening. Okay.
Yeah. Yeah. So,
Okay, Pratish. You have any doubt in this diagram?
no, no, no. I understood that whatever you told, no, that
Yeah.
it is
So if
somewhat what the position is there and where it is going.
going, yes, that is important. Okay, and Pratyush, for BLDC, uh,
Okay.
if you look for online material, multiple manufacturers will have different type of hall arrangement or
Mm-hmm.
trapezoidal
Mm-hmm.
diagrams, induced EMF diagrams. So be careful about that. Yeah.
Okay. Okay. Yeah.
All right, Pratyush.
Oh, thank you.